Welcome to the pipeline mechanical design. As you know that we were discussing about the natural gas transmission under the edge of chemical process utilities. Let's have a look about that what we discussed previously. We discussed about the natural gas transmission with the pipeline gas velocity and erosional velocity. Then we discussed about the optimum pressure drop for design and pipeline packing, determination of different type of gas leakage, wall thickness and pipe grades. We established the relationship between the wall thickness and design pressure and talked about the temperature profile. In this particular lecture, we are going to discuss about the mechanical design aspects of pipeline. Now, in which we will discuss about the pipeline design formula, expansion and flexibility in pipeline. We will discuss about the restrained lines, then unrestrained lines. We will discuss about the valve assemblies including the block valves, side valves. So, when we talk about the pipeline mechanical design, so first thing is that we need to establish the pipeline design formulation. Now, it is mostly used formula for determination of circumferential and axial stresses in the pressurized thin walled pipe. It can be developed by considering the vertical and horizontal force equilibrium, which we have shown in this figure. Now, here you see that this force equilibrium in a pressurized thin pipe. Now, in this particular figure, due to internal pressure P, a tangential force F, you see over here, is created in the pipe wall, and we assume it to act on per unit length of the pipe. The resultant force due to pressure is say Pd, and force acting in the wall is Pdi by 2. Now, this force is acting on an area of pipe wall which is A, and this is the product of wall thickness T and the unit length L of the pipe. So, therefore, tangential or hoop stress St in the pipe wall is F over A, and it is given as St is equal to Pd over 2T, and that is equation number 1. Now, for horizontal equilibrium, the forces which is shown in this figure can develop the longitudinal stress in the cylinder. The longitudinal force acting on the pipe and it is caused by the internal pressure. Now, the longitudinal force acting on pipe force acting on pipe, and this is caused by internal pressure, that is F is equal to P pi d square over 4. The longitudinal force is equilibrated by the force F P W in the wall acting on area approximated by pi dt. So, axial stress Sx is equal to P pi d square upon 4 pi dt, and that is equal to Pd 4 over 4t, that is equation number 2. Now, for most accurate formula of axial stress will be found by using actual area of the pipe wall bearing the longitudinal pressure force, and that axial stress Sx is equal to F upon pi d square minus small d square upon 4, and that is equal to P d square upon d square minus d square, and that is equation number 3. Now, where this capital D and D, they are the outer and inner pipe diameter. Now this is less conservative than using thin wall approximation. The bending section modulus Z of a thin walled cylinder, this can be approximated as where r, I mean if we take r as a mean radius, then Z is equal to pi r square t, or Z is equal to pi over 32 d to the power 4 minus small d to the power 4 upon capital D. Now this is applicable to thin wall pipe, where it is assumed that the stress is uniform throughout the wall thickness. Now such type of assumption is invalid when d over t ratio is less than 16. For thicker wall pipe, the radial stress varies from a maximum at inner surface to a minimum at the outer surface. Then an alternative formula should required in place of equation 1, which we have discussed earlier. Now, as we were discussing about the equation 3, this equation 3 illustrates an element of thick walled pipe for general case of an internally applied pressure Pi and external pressure, that is Pe. Now this figure represents the tangential and radial stress in a thick wall pipe. Now here you see Pe, and this is the internal diameter, internal radius. Now the expression for radial stress SR and tangential ST apply to the element of at any radius. Now ST is equal to Pi Ri square R naught O square minus R square plus Pi Ro square R square minus R I square over R square Ro square minus Ri square, and that is equation number 4. And SR is equal to minus Pi Ri square R naught square minus R square minus Pe R naught square R square minus Ri square upon R square R naught square minus Ri square, and that is equation number 5. Now in this equation number 4, which we discussed in this particular slide, the numerator will always exceed that of equation number 5. Now that is the tangential stress will always be larger than the radial stress. So when pipe is subjected only to internal pressure, then the previous equation becomes ST is equal to Pi Ro square plus R square upon Ro square minus Ri square, and that is equation number 6. So on substitution of say Ro in terms of Ri and T, and if we rearrange the equation, then it becomes St minus Pi T square plus 2Ri St minus Pi T minus 2 Pi Ri square is equal to 0, and that is equation number 7. Now if we solve these equations, then T is equal to d by 2 St plus Pi upon St plus Pi 0 to the power half minus 1, and that has become the equation number 8. Now these equations may be arranged to determine the bursting pressure of the pipe, which occurs when the tangential stress equal to ultimate tensile stress. Now, to calculate the wall thickness, to calculate the wall thickness of a pipeline, now this design formula can be used, that is P is equal to 2 St upon D FLJT, and that is equation number 9. Now, where P is the design pressure, S is specified minimum yield strength, T is wall thickness, D is outside dia of pipe, F design factor, J longitudinal joint factor, L location factor, and T is equal to temperature derating factor. Now, in this table, there is a comparison of design factor in North American courts. We have given the reference. Now, if you see that we have enlisted various applications like gas, and apart from this we have the Canadian Standard Association references and then ASME standards. So, if we take the design factor and location factor for CSA as well as the design factor for AMSE, then the general and seized crossing, general and cased crossing, the design for class 1 0.80 and class 2 0.72, and for class 3 it is 0.56. Now, if you compare with the AMSE or ASME codes, then the class 1 0.80, class 2 0.60 and class 3 0.50. Similarly, if we take the roads into consideration, it is 0.60 for class 1 under CSA and 0.50 in class 2 and 0.50 again in class 3, where ASME suggests 0.60 for class 1, class 2 0.50 and class 3 0.50 again. For railways, in CSA it is 0.50, 0.50 and 0.50 respectively for all three classes, and 0.60, 0.50 and 0.50 respectively for all three classes under ASME. Now, if we take the stations, then it is uniform across all three classes in CSA, and also in under ASME it is again uniform to 0.50 in all three classes. Now, if we take the general and crossing with respect to the roads and railways, there is a slight variation between these two standards, CSA and ASME. Another class is that high vapor pressure or liquid general cased crossing, in which the roads they are having the 0.64 and 0.64 in class 2 and class 3 in CSA, whereas 0.72 in all cases of class 3 under ASME. Similarly, if we talk about the railways, the class 2 and class 3 are 0.50 each in CSA and 0.72 each in ASME in all three different classes. Similarly, in stations, 0.64 in class 2 and class 3 and 0.72 is common for all three classes under ASME. Similarly, low vapor pressure liquid, that is RR crossing, then it is 0.80 and 0.80 for class 2 and class 3 in CSA, and 0.72 is common for all three classes of ASME. Uncased railroad crossings, it is 0.80 and 0.50 in class 2 and class 3 in CSA, and 0.72 is common for all three classes ASME. Now here you can see the comparison of longitudinal joint factors in North American courts, and again the seamless and again this is compared with the CSA and ASME, and seamless for CSA is 1.00 and it is similar to ASME. The electric welded the applicable code is CSA, that is 1.00. And similarly, if you see that submerged arc welding, again both the values are similar, and the furnace butt welded, both the values are similar. Apart from this, all the values are pertaining to ASME. Now, if we compare the temperature derating factors in both the references, then the temperature profiling from 120 to say 150, 180, 200 and 130, only CSA and ASME ratings are same. And similarly, if we take the 30 degrees Celsius and less than 120 degrees Celsius, in between 120 degrees Celsius, the ASME reported 1.00. Now, to calculate, if we take this ASME B31.82003, to calculate the wall thickness of a pipeline, now the design formula would be P is equal to 2ST over D FET, and that is equation number 10. Now, here F is the design factor based on location classification, we can refer to the table. Now, E is the longitudinal joint factor, and T is the temperature derating factor. Now, if we take ASME B31.42002, to calculate the wall thickness of a pipeline, the design formula would be P is equal to 2ST over D FE, and this is equation number 11. Now, again F is the design factor, (0.72), E is the longitudinal joint factor, and temperature derating factor T is 1.0, provided it is in lying between minus 30 degrees Celsius to 120 degrees Celsius. Now, T pipe is the pipe temperature. Now, the location factor in CSA Z662 and the design factor F in ASME B31.8 depends on the location classification of the pipeline. No equivalent factor is defined in ASME codes, where an allowable stress is defined as 0.72 SMYS. The longitudinal joint factor J in CSA Z662 code and E in the ASME code are generally 1 for commonly used pipe types. The temperature derating factor T is defined only in CSA Z662 7 and ASME 31.8. ASME B31.4 defines a range of temperature for which previous equation which we derived earlier is applicable. Now, let us talk about the expansion and flexibility. The expansion and flexibility in pipeline, the pipeline should have sufficient flexibility to prevent the thermal expansion or contraction due to excessive stresses in piping material or imposing excessive forces or movements on equipment or support. The flexibility should be provided by the use of bends, loops, offsets and mechanical joints or couplings. Now, if the expansion is not absorbed by the direct axial compression of the pipe. The flexibility analysis, this determines a suitable piping layout so as to minimize pipe stresses and evaluates the range of stresses which is encountered during the cyclic loading. The most common range is the thermal stresses range, and this is caused by the system startup and shutdown conditions. There are some fundamental differences in loading conditions for buried or similarly restrained portion of piping and above ground portions not subjected to axial restraints. So, different limits on allowable expansion stresses are necessary. Now, the ASME B31.8 code, it does not clearly differentiate between the restrained or unrestrained lines, rather it is operator's responsibility to define the type of restraint. Now, let us talk about the restrained lines. Now, if significant temperature changes are expected for buried lines, then it is necessary to calculate the expansion. Now, where the lines terminates, change in direction or changes in size, then the thermal expansion of buried lines may cause movement at that point. The hoop stress due to design pressure is determined by this particular equation, that is SH is equal to PD over 2T, and that is our equation number 11. Now, in the pressurized pipe, the radial growth of the pipe will induce an opposite longitudinal effect to that caused by the thermal effect. So, the longitudinal compressive stresses would be SLC is equal to VSH minus EC alpha T2 minus T1, that is equation number 12, where SLC is the restrained longitudinal compression stress, V is the Poisson's ratio, alpha is the linear coefficient of the thermal expansion, T1 is the ambient, and T2 is the maximum operating temperature. Now, to limit the combined equivalent stress on the pipe, SH minus SLC is less than equal to 0.9 ST, and that is equation number 13. Now, where S is the specified minimum yield strength and T is the temperature derating factor. Now, this equation is not applicable when SL is positive. Now, this equation lies in considering the biaxial state of stress in the pipe wall caused by the circumferential hoop stress and longitudinal stress. The failure will occur when the maximum shearing stress reaches the yield stress of the pipe material. Now, to reach at a maximum allowable shearing stress, SH minus SLC is reduced by the design factor, and in this case it is 0.9. Now, for portion of restrained pipeline that are freely spanning or supported above ground, the combined stress is limited and usually found by SH minus SLC plus minus SB less than equal to 0.9 ST, and that is equation number 14. Now, where SB is equal to absolute value of beam bending stresses caused by dead and live loads acting in and out of plane on the pipe. So, the value of SB can be found out by this equation, that is SB is equal to 0.75 II square plus 0.75 IO square plus MT over Z, and that is equation number 15. Now, where this Mi, Mo and Mt are in plane, out of plane and the torsional movement respectively acting on the pipe, and Z is the section modulus. I and IO is the in and out of plane stress intensification factors. Now, there are certain unrestrained lines. Now, the expansion calculations for above ground lines have to account for thermal changes as well as beam bending and the possible elastic instability of the pipe and its support that due to the longitudinal compressive forces. Now, in CSA and ASME, the stress due to thermal expansion for those portion of pipeline system without axial restraints are combined and limited in accordance with the formula, that is SB is equal to IMBZ, where SB is equal to resultant bending stress, I is the stress intensification factor, MB is the resultant bending moment, and Z is the section modulus of pipe. Now, for twisting, ST is equal to MT over 2Z, where SB is the torsional stress and MT is the twisting moment. The combined thermal expansion stress can be given like SE is equal to SB square plus 4ST square to the power 0.5, where SE is the combined thermal expansion stress. So, the limiting case must be satisfied like 0.5 SH plus SBD is less than equal to 0.54 S, and that is equation number 17, where SBD, this one is absolute value of beam bending compression stress resulting from dead loads. Now, limitation after addition of live loading, that is SE plus SL plus SBD plus L should be less than equal to S, and that is equation number 18. Now, where this SB D plus L is a longitudinal bending stress from both dead and live loading, and SL is the longitudinal stress PD over 4T, and SL plus SBD plus L is less than equal to 0.85 S. Now, when we talk about the ASME B31.4, the bending stresses due to the thermal expansion of for those portion of pipeline systems without axial restraint have to be combined and limited in accordance with the equation for T less than 120 degrees Celsius. So, SB is equal to IMI square plus IOMO square to the power half over Z, where SB is the resultant bending stress, MI is the in plane bending moment, I and IO is the stress intensification factor for bending in the plane and out of the plane of the member, MO is the bending moment out of or transverse to the plane of the member. Now, let us talk about the valve assemblies. Now, valve assemblies, let us first take up the block valves. The block valve assemblies are required to isolate the sections of main line or when isolation is required in event of a line break or if maintenance in a section of line is necessary. Their function is to provide a leak tight seal without experience undue deflection, and that is why they are stiffer than the adjacent pipe and their stress levels are half of the pipe. The ease of access and the site conditions should always be evaluated when selecting a location for a valve assembly. There may be certain required components, and if required a gate or a bulb valve or same size as to main line to allow the passage of pigs. Now, to blow down of gas either from remote or directly connected to main line interconnected for equalizing the pressure on both sides of the block valve. Usually a riser on each side of the block valve is there to provide a power supply for hydraulic or pneumatic operator or for taking fluid samples and to connect the pressure gauges or to perform the flow test. Now, here you see that the various code requirement for the maximum block wall spacing. Again, the reference is CSA Z662 2007 and ASME B31.8 2003. Now, here you see that different type of class locations enlisted, and the gas pipeline, HVP pipeline for this, and this ANSI code B31.4 and ANSI B31.8. Now, here see that different classes are enlisted with the different distances. Now, let us talk about the side walls. The purpose of a side wall assembly is to isolate a lateral from the main line in situation where a line break may occur or when maintenance of a lateral may necessary. Now, there are various component required for this one. One is a gate or a ball valve of the site of lateral, check valve and bypass line, blow down with appropriate valve, flanges and insulation set to separate the lateral from main line, and test leads from the main line and lateral. Now, the check valve in the assembly is to prevent reverse flow and also to prevent the flow from main line into the inflowing lateral when the pressure in lateral is less than that in the main line. The location of side valves, it is necessary to locate the side valve assembly on the lateral immediately adjacent to the main line. Now, let us talk about the blowdown for gases. Now, it is used to vent gas to atmosphere, to expel air during purging and to hook up a pull down compressor. Now, when locating a valve assembly with a blowdown, then it is important to choose an area that has no building immediately downwind and contains no source for igniting vapors. The blowdown and valve assembly, it should be enclosed in fenced area to protect them from any kind of damage. The blowdown size is governed by the time available, that is 30 to 60 minutes generally, for depressurize the section of line. Now, sometimes you need to know the formula for calculating the blowdown time. So, blowdown time, that is referred as Tm, is equal to 0.0588 p to the power by 3 P1 g to the power half d square LFC upon d square, where Tm is the blowdown time in minutes, P1 is the initial trunk line pressure, G is specific gravity of the gas, D is the internal diameter of trunk line, L is the length of trunk line being blown down, D is the internal diameter of blow down stack, FC is the choke factor. For ideal nozzle, it is 1.0. For full port gate valve, 1.6. Reduced port gate valve, it is 1.8. And regular plug valve, it is 2.0, and Venturi plug valve, it is 3.2. Now, valve selection for the pipeline application. The mainline valve fulfill three main basic functions such as sectionalizing, diverting and segregating. Now, sectionalizing is required to minimize and contain the environmental effect line rupture. Now, when line is interconnecting, then valves are required to divert the product flow to meet production line. The valves provide segregate or isolate process equipment such as scraper traps, entire plant for safety, maintenance and operating reasons. Now, the gate and ball valves are utilized in the pipe transmission. Here you see the gate valve and ball valve which are used in various kind of a pipeline operation. Now, there are certain variables that must be considered for each valve installation, and these are the what are the different operating characteristics one must know, what is the function required and where they need to be located, then fluid services, which kind of the fluid services need to be done, then materials option, space available, maintenance and repair capabilities, delivery schedule, cost, etc. So, all these factors or a variable must be considered while considering all these things. So, at last in this particular segment we discussed a lot of about the gas transmission, especially natural gas transmission, and for your convenience we have listed couple of references. If you wish to have a further reading, you can seek the help of all these references. Thank you very much.